Alright, ladies, today we are going to be starting the beginning section of Chapter 7. Last night for homework, you read an article about how as humans we kind of interpret risk, and as you hopefully got out of it, a lot of times we under or overestimate the danger to ourselves in various situations. Just a minute ago, I had you do the Monty Hall problem, or a simulation of the Monty Hall problem, where you had to decide whether you were going to stick or switched. Oftentimes, with this problem, people usually want to stick with or stay with their original choice just because you've been taught all along that going with your first instinct is usually the best. However, after years of collecting this data, I found that most often the people who, when they do the switch strategy, end up winning the big cash prize more often than not. So even with something unlike Risk, where it's actually more of a reward, our intuition doesn't necessarily pan out mathematically in terms of what is in our best interest. So let's take a look at a couple other myths of kind of intuition versus probability. These notes are on OneNote for you if you don't already have them open, and then we'll talk about how mathematically we get around that rather than using our intuition, how we can use some other things to figure out how likely various events are to occur. So here are the myths spelled out for us in the beginning of our textbook. The first myth of 3 is a myth of short-term regularity, and that is the idea that if something, for instance, flipping a coin, is predictable in the long run, we think it should be predictable in the short run as well. So, for instance, if this first example, we have flipping heads and tails, head, tail, head, tail, tail, head. Is that more or less likely than tail, 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 head, head, head? Most of us would choose this first one as being more likely to occur just because we figure that coin tosses are random, therefore should have more of an alternating pattern, when in reality, of course, the coin does not have a memory, so these two different set of 6 coin flips are actually equally likely. Just kind of like our Powerball discussion the other day, people were debating on whether they should pick their own numbers or have the machine pick. Technically, the ping pong balls that are bouncing around have no memory. Therefore, it should actually be the same likelihood of winning in either case, whether it's the machine pick or your own pick, birthdays or whatever. Okay. Likewise, if you are into watching or even participating in sports, there is the myth of hot streaks. So people that get on a streak of hitting lots of free throw points or something like that, or if they're going through a cold streak where they're missing a lot in a row, gets attributed to luck or a streak of some sort, rather than just realizing that you may have several of the same occurrence or event happening in a row, but that doesn't necessarily mean that the long term will be any different. It will all balance out in the end. Second myth is the myth of the surprise meeting or the coincidence, and that is, for instance, running into someone you know in an unexpected place. So, for instance, running into a friend of yours from grade school when you were out on spring break in Florida. And while it may be unlikely that you yourself ran into that one particular person when you were on spring break, the fact that a lot of us are on spring break at the same time, a lot of people from Louisville do end up going to this very similar areas of Florida, it doesn't end up being that unlikely, probability-wise, that you would run into someone that you would have some kind of connection with, whether it's grade school, high school, church youth group, whatever. Okay. Likewise, while there haven't been too many big-time winners, it is mathematically possible that somebody could win the lottery twice. Very luckily, yes, but not necessarily even a rigged system. So while it's unlikely for any one individual to happen, the likelihood for an individual to win the lottery twice in the course of all the lottery drawings nationwide that go on an annual basis is not all that unusual. And the third myth, I went kind of in the order that the book gives. It actually is probably more associated with or contrasting with the myth, the short-term average, is kind of going in the opposite direction. So the myth of the law of averages says that if you have a run of several things in a row, that you are due for the opposite event. So for instance, if I'm tossing a coin many, many times, first of all, I would think it's very strange that I would get 6 tails in a row. But once again, assuming the coin isn't rigged, that could just be a short-term run. Some people would want to say, well, then you're more likely to get ahead on the next toss. But once again, of course, the coins have no memory, so it doesn't matter to the coin how many times it's just tossed heads in terms of, or just tossed tails in terms of turning ahead the next time. Each time, regardless of what the previous events have been, you should have a 50-50 chance of getting heads or tails. Likewise, if you've ever been at a church picnic or a community festival where they have something like a cake booth, and people see that number 31 won, that person won a cake last one. Most people will not bet on number 31 again because 31 just won. It can't possibly win again. Whereas if you actually thought about it, the spinning wheel has no memory in terms of the fact that 31 just was a winner, and therefore as long as it is spun properly and isn't rigged, 31 should be just as likely to come up on the next spin as any of the other numbers on the wheel. So how do we deal with calculating the likelihood of probability if our intuition and culturally we are taught things that don't exactly mathematically pan out? What we're going to talk about today is one method for figuring out how mathematically likely something is to occur, and that's called a simulation. We will do some other probability rules later in the chapter, but this is just a way, similar to that Monty Hall simulation that you just did, that we can imitate chance behavior without getting into the rules just yet. So first definition is the definition of simulation. You're welcome to pause the video here if you need to, but the definition of a simulation as given by our textbook is a type of experiment that imitates chance behavior. So this will be something like tossing a coin, using random numbers in a calculator or random digit table, rolling a dice, using a computer program like what we just did with Monty Hall to imitate someone opening doors as opposed to actually having the doors open themselves. In order to carry out a simulation, it's just 3 steps really that you have to spell out. First step is you will state your assumptions. So for instance, for the Monty Hall problem, the prize is equally likely to be behind any door, any of the 3 doors. In other words, the prize's location is independent. The people are not rigging the game. They aren't changing where the prize is. Once that first door has been chosen, that would need to be stated up front. Likewise, if I'm tossing a coin, I would state that I would expect the probability of any coin flip to be 50-50 heads versus tails. Okay, I'm going to scroll down just a little bit, jump down to the definition of independence, and we'll finish with the other 2 steps in just a minute. Independence just really means that the results of one trial have no effect on the next trial. So once again, when I flip a coin once, it has no memory. It does not know whether it got heads or tails last time when I flip it again. Okay, so it does matter, for instance, that for the Monty Hall problem, that where the cash prize was placed would not matter based on where it was the last time or what the contestant chose. Okay. Step number 2, we're going to assign digits. Okay, so if I'm using something like a coin, that would be head versus tail. If I'm using rand_int or random number table, that would be assigning my zeros, ones, and twos to represent outcomes. That'll be very similar to what we did in our experiment chapter. And then I'm going to carry out the simulation using random digits or a coin or a dice or some other random device. And I will see how likely it is that the digits I'm looking for turn up in my simulation and draw a conclusion from that. Okay, so first example here. This is on page 322 if you wanted to snip kind of a better description than what is here for you into your notes. But we have Shaq has a free throw percentage of 50%. How likely is it that he makes at least 3 of the next free throws out of 10 shots? So our assumptions are that he has a 50% chance of making a basket and each shot is independent. So in other words, he doesn't have a high, if he gets one in, he doesn't psych himself up to get and make him more likely to get the next one. Likewise, if he misses one, he doesn't psych himself out and get depressed or something and make himself less likely to get the next shot. I chose to assign digits where the evens, single-digit evens, would represent Shaq's success and the odds would represent failures. Going down to my table, and once again, feel free to pause anytime you need to. For the first set of 10 numbers, notice this one just goes by 4 digits. So the first 10 numbers is 5551, 5412, 37. So that's where, the first 10 numbers are, and there are only 2 even numbers in that. So out of those 10 shots, he only got 2 through the net, 2 successes. In the next 10 shots, he ended up having a 6, a 4, a 0, and a 4. So I got 4 successes out of the next 10. The next 10 shots, he got 6 successes, 6 even digits. The next 10 starts here and then moves on to the next line. He got 4 successes, and then in the final trial, we got 4 successes. Okay, now usually you'll be told how many simulations you do for the particular problem. In this case, I did 5 simulations. So I did 5 trials of 10 shots each. And my conclusion would be out of the 5 trials, Shaq made at least 3 free throws 4 out of the 5 times, or 80% of the time. So if I was looking at somebody with a 50% free throw average, how likely is it that they would get at least 3 free throws out of 10? I would say it's very likely. Okay, it's the majority of the time, by far, we would expect that to happen. Okay, and I could use that if, for instance, someone who usually has a 50% average suddenly was only getting 1 or 2. Maybe that player is injured or something else is going on. Just real quick, let's talk about assigning digits here. I could have just as easily switched the evens and the odds in terms of which meant success, which meant failure. I could have instead used 0 through 4 to represent success and 5 through 9 to represent failure, as long as I had the same number of digits representing success and failure. That would have represented the equally likely chance that he would have either made or lost the shot. I could have also done a coin flip or a dice with evens and odds, even success and odd not, or 1 through 3 success, 4 through 6 not, and so on. Okay, if I have something like this where I'm talking about internet connection, since it's not equally likely I have 80%, I would just need to make sure that 80% of my numbers represented having internet and the other 20% representing not. So I could have picked any 2 numbers out of the 10 to represent not having internet, 0 and 1, for instance, instead of 8 and 9. Okay, this last one that I'm going to show you here is the toughest one, where I have it kind of not an even multiple of 10, and I would have to just make sure that 83% of my numbers represent internet versus no internet. So it could be 0 to 82 or 1 to